Now we will discuss some of the basics of control systems from these notes, which are basically derived from the book Norman S. Nice Control Systems Engineering 6th edition. Okay, so what is control? A definition: manipulation of a system's input to achieve a desired output. You want a desired output. Basically, desired output comes from the feedback control, where we have a feedback, where we have a set point. As I already explained in the previous lecture, that there are two types of control: feed forward and feedback. Can you mute your mic, please? If you have any question, then you can okay, you can speak when you can unmute when you want to speak. Okay, so manipulation of a system's input to achieve a desired output. So this diagram is like open loop control system. You give input to the system and you get output from the system. It's just like an on off button in your house for a sprinkler system or for any tube lights, where you give input and you get output. And similar like here, acceleration pedal position, you give input and you get output. But if you want an automatic control system, you want the system to automatically achieve a desired set point, your desired level, your desire. So for that system you need a feedback. Okay, you need a sensor to monitor your desired variable to compare with a set point. So from that comparison, a signal is generated, which is known as error signal, which then goes to the controller. And you can design a controller to be like on-off controller, proportional controller, integral, PI or PID controller. These are the very basics controller. Now we are not dealing in research. For example, in advanced research, we deal with the advanced forms like sliding mode control, optimal control, robust control. So in this course we will be just sticking to the basics like on-off control, proportional, integral, PID control. Okay, so either controlled directly or automatically by the cruise control. So cruise control is a control for controlling the speed of the car, where we have a set point, where we have an offset also, because if we achieve a set point, then error signal will be 0. When error signal is 0, if the controller generate the output 0, then your car will stop. So you need a certain bias to make your car speed run at that desired speed. So that is the cruise control. Okay, that's just for the idea. Now we come to our content. Open loop control is scheme where the output has the influence on the input. You give input and you get output. Simple. It's toaster like. You can't accident for disturbance as well. You can't account for disturbance as well. It is not a good control. You apply this control where you have a pretty much simple system, and you know that if you give certain input, you will get the certain output, which will not go out of bound or make your system unstable. You already know the behavior of the system. That's why you give calculated input and you get calculated output within bounds. But this is the limitation. This is not a good control. So good control is closed loop control, where you have the feedback scheme where the output is fed back to affect the input. Like for example, you want to control the speed to some desired variable set point. So what you will do, you will install a speed sensor to monitor that speed, and you will compare with the desired value. If there is some error, it goes to controller generates an output which is known as manipulated variable, which is the input to your actuator. This is your actuator vehicle, and that vehicle basically influences that speed, which is again monitored by the sensor, and the loop continues until the error signal becomes 0. Our purpose in this control system is we want to make error signal equal to 0. We don't want any error. If we want the speed of 70, we have the 70, we must have here 70. We do if this is 70, this is 70, error will be 0. So in this control system, the objective will be to make this error equal to 0. This will be the purpose of this feedback control system. Okay. Control design objectives to get error to 0. Okay, error to 0. Steady state response is the state of the output error after transients have died out. Steady state response, there are two types of responses: transient response and steady state response. Transient response is momentary response, like you give input and you get output up to a certain limited amount of short period of time. very little time the moment you give the input. But the steady state response means theoretically at t is equal to infinity, like after so much time, for example after 5 tau, the system goes into the steady state. So state of the output error after the transients have died out, ideally 0. So the steady state error ideally should be 0. If you have the desired set point of 70, you must get 70. If you get 68, that means there is some error, there is some steady state error, there is some offset. So we want that offset to be 0. A good control system makes the offset to be 0, but this is possible only with the integral control. A proportional controller cannot make your offset equal to 0. We will discuss it later when we have some basics about control system. So we normally have PI controller, proportional plus integral controller, that makes the steady state error equal to 0, and that has a good transient response, a PI controller. Okay. Immediate transient response is the immediate response of output to a change in input. And stability, this is the most important part of any control system, that our control system must be stable. If our control system is not stable, it is of no use. For example, you are sitting in a car and the car is not in your control, it goes out of control. You give command to your throttle, your pedal, but the car speed becomes very high, like 200 kilometers per hour, and it strikes with some tree, with some other vehicle. So this is an unstable system. You want complete control over your system. So for that purpose, your system must be stable. You must be able to control its parameters, you must be able to control its time response, you must be able to control its speed, you must be able to control its overshoot. So that is the basically we want. By studying this course, we shall be able to have these skills, that if we encounter any system, any industrial system, any system in the lab, any system in the real world, we must be able to control it. Okay. So stability means it also means bounded input. If we give the bounded input, we get the bounded output, like Bibo system, you can say it bounded input, bounded Bibo, bounded input and bounded output. You give bounded input and you get bounded output within bounds, that it remains in bounds. Okay. We will discuss further it later. There are various criteria like Routh-Hurwitz's criteria, and then we have the frequency domain like gain margin, phase margin, Bode plots. So these are the classical techniques by which we determine the stability. There is some advanced techniques which are being used in research, especially I have used is the Lyapunov stability theorem. That is another part, but it will not be in this course. Okay. So modeling the physical system, this is the most important aspect of a control system, that we must be able to model it. We must be able to write differential equations for the system. Modeling means you are writing your the differential equations, you are writing your you are able to model it, you are able to make equations that behave just like your actual system. This is the definition of model. Model means an abstract thing which behaves like an actual system. If you give the input to the actual system, you get the output. So if you give the same input to your model, you must get the same output. That is the model accuracy. Your model must be accurate. Okay. So differential equations and Laplace transfer functions, that we already discussed in the previous lecture. Why this Laplace is being used? It is being used to solve this headache, basically this differential equation, that if you have a complex differential equation, it will be difficult to solve it through mathematical means. So Laplace transform provides a means to solve it in a simple way, and then we take inverse Laplace, and from time domain we go to the frequency domain, and from the frequency domain we come back to the time domain, like the mask I gave example in the previous lecture. Okay. Modeling. In this class, linear time invariants and linear systems means there are two types, basically there are two types of systems, linear and non-linear. Linear means, basic definition of linearity is the basic definition I would say let's use this quote. Okay, I read here. So what is a linear system? x and y depends on x. So if you change x, y changes proportionally. So that is a linear system. That is delta y is equal to some m dot delta x. The m is your gain, that is your linear system. And what is a nonlinear system? Nonlinear system is you change x linearly, but you get the change in y non-linearly, like square. This is like y square, or like this in terms of under root. So that is a kind of a non-linear system where you don't get the change in your system linearly. Okay, if you change x, if you get the change in y linearly, that is a linear system. Mostly we deal with, in this course we deal with, we assume our system is linear, because if for example if we have a non-linear system, we divide it in intervals, like this interval, small intervals, in which it behaves like a linear system. But actually practically every system is a non-linear system. Also simple, I would say 1 plus 1 equal to 2. We say that 1 plus 1 equal to 2. That is a linear system, but practically 1 plus 1 never equals to 2. So it sometimes it becomes greater than 2, sometimes it becomes less than 2. So that is the meaning of a linear and non-linear system. Okay, linear time invariant. Time invariant means its parameter do not change with time. Like its parameter do not change with time. You get the same, if you give the same input, you will get the same output, no matter you apply it later or earlier, you will get the same output. That is the time invariance. There is no effect of time on the output of the system. Okay, that is our assumption. We are dealing with this kind of systems in this course. So Laplace transform is Laplace of f of t is f of s. This is the time domain function. We applied the mass and we got f of s in frequency domain. That is the powerful, you can say, powerful to solve it. So what it actually means, f of t multiplied by e raised to power minus st dt, and we integrate it from 0 to infinity. That is the basic definition of a Laplace transform. You remember that in the last lecture we had a simple table which we must have memorized in our mind. So that table was basically built from this formula. This is the main formula from which that table was developed. Okay, so f of t is the time domain signal, f of s is the Laplace transform of the f of t, and complex frequency s. What is s? S is basically equal to sigma plus j omega. Sigma is your real, it's a complex number. You know about complex number a plus b iota. What you have, this is the real part and this is the imaginary part, and what will be its magnitude? Under root sigma square plus omega square. Okay, and what will be its angle theta? For example, we have two forms of complex numbers, like this is a not regular form and there is a polar form where we have r angle theta. R angle theta, r is the magnitude, which is under root sigma square plus omega square, and theta is basically tan inverse omega over sigma, tan inverse imaginary part over real part. Okay, so the formula for the inverse Laplace transform is this formula. If you take the inverse Laplace of f of s, you will get f of t and 1 over 2 pi j, and its integration will be sigma minus j omega to sigma plus j omega f of s t e raised to power s t ds. This is the formula. So basically which we apply from the table, we apply the Laplace transform and inverse Laplace transform. These are basically derived from these two formulas. These are the building blocks of the basic Laplace theorem, Laplace transform. Okay, e raised to power sigma plus j omega, we can split it like e raised to power sigma t into dot, because you know that this is the theorem, mathematical theorem, that if you have the same what you call it, that if you have the same this constant is, if this constant is same, then its power are added. Okay, so e raised to power sigma t e raised to power j omega t, and e raised to power j omega t, what you can this is the Euler's theorem. Okay, e raised to power sigma t is equal to cos of omega t plus j sine of omega t. Okay, so e raised to power cos of omega t plus j, from where it came from, this is the derivation of this e raised to power j omega t. Okay, cos of omega t plus j sine of omega t. This is Euler's theorem. It is basically, it is the basic representation of any complex number. So you don't need to drive it, you just need to accept that it is like this. Okay, now f of t is equal to 6 into e raised to power minus 2t ut. Now if you take the Laplace transform of this thing, what will you get? 6 into e raised to power minus 2t e raised to power minus 2t, it will be 1 over s plus 2. And u of t, what is meant by u of t from these things are basically not explained in these notes, but in the previous lecture I tried to explain the u of t parabolic function, like u of t is first is impulse, then you get across this step function, and then comes the parabolic function, and then comes the ramp function, and then comes the parabolic function. If I open the book from Norman S. Nice, you can see here. Okay, here you can see I show you some these inputs here, like these are the theorems. Okay, the table, this is the basic table from the book. Okay, this is Laplace transform theorem, and what we were discussing, yes, this. Okay, this property is very much important. This is basically frequency shifting theorem. If you shift the frequency like s plus a, this is frequency shifting. It is basically it what happens in the time domain, you multiply it with the negative of that thing, that shifting, like e raised to power minus at f of t is f of s plus a. This is frequency shifting theorem. And for the time shifting theorem, like t minus capital T, you will get e raised to power minus st into f of s, the same sign, minus minus, but here it's a plus, but on the left side you have the minus. That is very important property here. Okay, so 6 into e raised to power minus 2t and u of t. U of t is, we know that u of t, the Laplace transform of u of t is 1 over s, and if you have multiplied by it minus 2, it will become 1 over s plus 2. Okay, so that will be 6 into over s plus 2. Here you will get s plus 2, it's 2. And if you have 6 into e raised to power minus 2t t minus 3, okay, here you have the time shifting here as well. Okay, so 1 over s t minus 3, here you will get e raised to power minus 3s, like this formula, e raised to power minus 3s. Okay, here e raised to power minus 3s, here t capital T, here it is 3, so here you will get minus 3s, and e raised to power minus 2, it will become 1 over s plus 2, so it will be 6 into e raised to power minus 3s over s plus 2. It's not alpha, it's 2. Okay, so this is the time shifting property. Time shifting property minus capital T u of t minus capital, that is e raised to power minus s t. So is that okay here? Should I proceed further, or if you have any question, you can ask. So this table, like this theorem table, the definition, and then you get the linearity theorem. If you multiply it with any constant, you get the same constant multiplied by in the frequency domain. Here is the time domain, and this is the frequency domain. If you add up these functions in the time domain, you get your frequency. In the frequency domain, these functions get added. And if you shift your frequency, you have the multiplication with this exponential e raised to power minus 80, the opposite sign. That's the important point, opposite sign, s plus a e raised to power minus 80. Okay, if here is s minus a, here you will be having e raised to power plus 80. Okay, and in the time domain, t minus capital T, now it will have the same sign. Like if you shift in time domain, you will be have multiplication with the exponential. These exponentials are very important in the electrical engineering. You encounter, I will explain further when we will move to the response of a second order control system. Okay, so it is from minus s t. Now look at this, the same sign, minus t, here you have minus t. If plus t, you will have plus t. Okay, now if you multiply a with t in the frequency domain, you will have 1 over a f s over a. Okay, multiplication in the time domain will cause division in the frequency domain. These two domains are opposite. Okay, now this is the derivative Laplace. If you take the Laplace of the derivative of function, you will have s into f of s minus f of 0 negative, minus f of 0 negative. So normally we make this initial condition as 0 normally. So to make our life very easy, it becomes just one derivative s, 2 derivative s square, 3 derivative s cube. Okay, but actually it's basically s square f for example, for the second derivative, it's s care f capital f of s minus s into f of 0 negative. 0 negative, what is 0 negative? It's the initial condition, okay, and minus f dash at 0 negative. This is the complete formula of second derivative, and the question becomes very much complex when you are given these values, okay, because you have to put these values into your system to get accurate answer. If the question is like you have assumed these values as 0, for example, you have a capacitor which has no charge, initially no charge, or if you have an inductor which initially has no current in it, so that what it means, initial conditions, okay. So this is a generic formula, it is derived from these two. Like for the higher orders, you can get, if you put here 2, you will get this, if you put here 1, you will get like this, okay. And this is also important, this is the integration theorem. Here if you take the derivative, you multiply with s, but if you take the integration, you divide by s, okay, you divide by s. In the frequency domain, you divide by s. And then comes two very important theorems, that is the final value theorem. For example, you want to determine the steady state value, you put t is equal to infinity. So in the frequency domain, you have s into f of s limit s approaches to 0. That is the formula. We will use this in the steady state error calculation in the chapter 7, when we will calculate the steady state errors for a system like type 0 system, type 1 system, type 2 system. Now we will like to determine that whether the system can be controlled with the step input, ramp input, or parabolic input. Will there be some steady state error? Will the system be able to track the input? Track input means able to follow the command, okay. We will discuss this in very detail in chapter 7. So this formula is very important, final value theorem. F of infinity is basically equal to s approaches to 0, infinity 0, okay, s into f of s. Initial value theorem, that's the opposite, like f 0 positive, initial value, here infinity, limit s approaches to infinity, s into f of s. Time period is basically 1 over f. So time is the reciprocal of frequency, it's the, you can say, opposite of your frequency, okay. So this table is very much important for the control engineer, okay. Now assume the numerator order is lower than the partial fraction expansion. So that is another now for example, if now this is the partial fraction expansion here, for the partial fraction expansion. So basically in the Laplace transform, we make it's easier to solve any system with the Laplace transform. So what we do, basically we do the partial fraction in the Laplace transform. For example, if we have f of s like 2 over s plus 1 into s plus 2, so we will we will separate these fractions, okay. So like k1 over s plus 1 and plus k2 over s plus 2, and okay. So this is basic, it's from the basic elementary math, yeah, that you divide your these common fractions into your partial fractions, and then you take the inverse Laplace, and when you take the inverse Laplace, it becomes easy to solve. For example, 2 over s plus 1 into s plus 2, you make the partial fractions like k1 over s plus 1 plus k2 over s plus 2, then you multiply both sides with these s plus 1 and s plus 2, you get 2 into k1 into s plus 2 plus k2 into s plus 1, then you put s plus 1 equal to 0 and s is equal to minus 1, then you find k1, okay. And when you put s plus 2 equal to 0, you find k2, and when you find k1 and k2, you get k1 like 2 and k2 like minus 2. So here you will have 2 and here you will have minus 2. So you will make your inverse Laplace. So inverse Laplace of 2 over s plus 1 will be 2 into e raised to power minus t plus 1, okay, minus t, and minus 2 into e raised to power minus 2t, okay. Here plus 2, so it will become minus 2, like plus a, it will become minus a. So this is the answer, 2 into e raised to power minus t minus 2 into e raised to power minus 2t into ut. Ut means because of this 1 over s, it's basically frequency has been shifted. So you can see that, yes, inverse Laplace, you can see that that theorem applied, basically this one, okay. This is very important theorem and very important theorem, okay. Okay, if you have a question like this, you have a differential equation like d2y over dt square plus 12 d by y dt plus 32y equal to 32u. You have a system, second order system. This is a second order system in which you will be having two energy storage elements. Okay, you have two energy storage elements in it. So how will you solve it? You are given the initial values as 0. Let me open it from which page is 39 page. Let me open it better page. Yeah, look, now it's very much clear. So just apply it. Initial conditions are 0. Your life is very much easy. You are given that the initial conditions are 0. So just take the Laplace transform. D2 it becomes s square capital Y of s and 12 into s into capital Y. Okay, one derivative 1s and plus 32 capital Y equal to 32 u of t. The Laplace of u of t is 1 over s. Okay, so you get 32 over s. So take the y common, you will get s square plus 12s plus 32 divided on the other side, you will get 32 over s into s square plus 12s plus 32, and then here you need the partial fractions. Okay, so you can solve it from your basic mathematics, like if you need to further simplify it in its roots. Yes, you have you have to apply factorization, like 8 into 4. If you multiply it, you get 32 plus 32, and if you add these, you get 12. Okay, so s plus 4 into s plus 8, these are the roots. Now you have to split these roots for the, you have to apply partial fraction. So you will have to apply like this, 32 like 32 over s into s plus 2 s plus 4. So a over s plus b over s plus 2 plus c over s plus 4. Now cross multiply it. Open some new window here. Okay, cross multiply it. You will get like 32 equal to first make it a bit simple. 32 over s into s plus 4 into s plus 8 equal to a over s plus b over s plus 4 plus c over s plus 8. Now cross multiply it with this denominator. You will get here 32. Here you will get s plus 4 and s plus 8. Okay, plus b into s plus s into s plus 8. Okay, plus, because that s plus 4 will cancel the other s plus 4 in it. Okay, got my point? S into s plus 4. You are basically multiplying this equation with this denominator. Okay, here it gets cancelled fully, you get 32, and here you cancel s with this and you get s plus 4 s plus 8, and here you get to cancel with s plus 4, you get s into s plus 8. Now if you want to determine a, just put this its denominator equal to 0, put s equal to zeros. Okay, you get 32 equal a into 4 into 8. Okay, this s is 0, this is 0 and this is 0. So you will get 8 into 4 32, you will get a is equal to 1. Okay, let me enlarge it. Now for b, put s equal to minus 4, put that thing is equal to 0. If you put this equal to 0, you will get b. So when you get b, 32 equal this term s plus 4 equal to 0, this term will be 0 and this term will also be 0. So here you will be getting b into minus 4 into 4. Okay, 8 minus 4 is 4. So b will be equal to 32 over, that is minus 2. b will be minus 2. 4 into 4 16 and it will be half. 32 over 16 is 2. Okay, minus 2. And what will be the c? Put s is equal to minus 8, you will get the c like c into minus 8 and minus 4. and c will be equal to minus minus plus, and 32 cancel, it will become 1. So you will get here your equation as 32 over, is my screen fully visible to you? Okay, sorry, it's s plus 4 into s plus 8 equal to, what is a 1 over s plus, what is b, it's minus 2, so make it minus 2 over s plus 4, and what is c, is your 1, so 1 over s plus 8. So now take its inverse Laplace, so you will get here 1 over s is 1, minus, that's basically u of t, we will take it common, and that will be minus 2 into e raised to power minus 4t minus 4t, okay, it will be minus 4t minus 4t and plus e raised to power minus 8t, that will be your time domain response, okay. This is your frequency domain response and this is your time domain response, okay. So let me open from the book, so you can see that 32 over s into s plus 4 s plus 8, that is k1 over s, k1 over k2 over s plus 4, k3 over s plus 8. So k1 you got 1, k2 you got minus 2. I basically put a b c here, the book has written k1, k2, k3, you can name it, it's the same thing exactly. So you have like this, y of s is equal to 1 over s minus 2 over s plus 4 plus 1 over s plus 8. Now take its result. I think yes, it depends on you. If you want to, it's better to follow the teacher's way. If the teacher has used in partial fractions like case, you should use the same, so that you remain as close to his approach as possible, okay. So 1 minus 2 into e to the power minus 4t and plus e to the power minus 8t into u of t, so that will be your output. Now you can see that this is the solution of this differential equation. If you solve it in a regular way, in a mathematical way, it will be very difficult, but you solved it through Laplace and you saw that it was very easy. It's just a piece of cake. It's just a basic elementary mathematics that a schoolboy of 12th grade can solve these things easily for the mathematics. So this is the benefit of the Laplace transform, that if we have a second order system like this, we can find its time domain solution by converting it to the frequency domain and then coming back from the frequency domain to the time domain, okay. So that's a very good example for this, and let me see if I have, so this is another example, a very good example. For example, the question is, these are from the book, okay, the book the course book, the textbook, okay, and these are very important, very simple and very awesome examples, I would say, to explain the things in a very simple way. So if you have the system as dc over dt plus 2ct into r of t, basically r of t symbol we usually for the input r of t, and for the output we have y of t or c of t. Both symbols are used, like y of t or c of t, and for the input we use x of t or r of t, okay, x of t or r of t. Both these symbols are used in this course. So if you take the Laplace here, what will be its Laplace? S into capital C of s, okay, plus 2 into C of s, and r of t is r of s. Take C of s common, that will be s plus 2, divided here and make r of s here. So cs over r of s, that is your transfer function, and transfer function is equal to 1 over s plus 2, okay, 1 over s plus 2. Okay. So this is the transfer function. The question was, find the transfer function represented by the differential equation. So this is the transfer function. G of s is equal to c of s over r of s is equal to 1 over s plus 2. Okay. Now another question we go through is, use the result of example 2.4 to find the response c of t to an input r of t. This is the input u of t, step input, assuming 0 initial condition. So we got this transfer function. Just multiply this r of, take this r of s here. Okay, so what will be happen, c of s is equal to 1 over s plus 2 into r of s. So what will be r of s? It will be 1 over s. Okay, r of s is 1 over s. So what you will get, 1 over s into s plus 2. Okay, 1 over s into s plus 2. Okay, this c of s is equal to r of s into g of s. R of s is 1 over s. Why 1 over s? It's step input. You have step input. If you had impulse input delta, you would write 1. If you have ut, you would write 1 over s. If you have here ramp like t into ut, you will write 1 over s square. Okay, for the, please you must have to remember this from this table. You must have to memorize this. Okay, and if you have a parabolic, then you have s 1 over s cube. Okay, so r of s into g of s. R of s is 1 over s and 1 over s plus 2 comes from here. So here you will get c of s. The question is basically asking c of t. So first you have to find c of s and then you will take its inverse Laplace. Okay, so c of s will be 1 over s into s plus 2. Now take its partial fraction. If you do the partial fraction, you get this. Okay, 1 by 2, it's k1 and it's k2. Okay, k2 is minus 1 by 2, k1 is 1 by 2. 1 by 2 over s minus 1 by 2 over s plus 2. Now take its inverse Laplace, that will be 1 over 2, 1 over s. What is the inverse Laplace of 1 over s? That is 1. Okay, 1 minus e raised to 1 minus 2t, because you are shifting frequency. So it will be e raised to 1 minus 2t. So c of t is 1 over 2 minus 1 by 2 e raised to 1 minus 2t. Please tell me if you do you understand this completely? If you have any doubt, you can ask question. Any doubt? Previous question. Yes, this is g of s. Yes, this is g of s. You got it from this differential equation. Yes, this is your differential equation. This is given to you. It's given to you. You have modeled a system, and this is, look, find the transfer function represented by this. Okay, the g of s is the transfer function. Transfer function means output over input in the frequency domain, not in the time domain. Okay, so you have to convert this t into s domain. So you will take the Laplace of dct, it will be s into c of s. Okay, s into c of s, and here it will be 2 into c of s, and it will be r of t is r of s. Okay, now take c common, you will get s plus 2. Take this common, s plus 2. Should I solve it on board, or is it okay here? Okay. Let me solve it slowly. You have you have the differential equation here, dc of t over dt plus 2 into c of t is equal to r of t. Now take its Laplace, so it will be s derivative, because its derivative we will have s into c of s. Initial conditions are 0, so therefore minus 0. Okay, it will be nothing here, plus 2 constant. Here we will be having c of s, r of t, capital R of s. Okay, in time domain we have small symbols, in frequency domain we have capital symbols. So now take this c of s common here, take this c of s common here, we'll be getting s plus 2 into c of s is equal to r of s. So c of s over r of s is equal to 1 over s plus 2. Cross multiply, you make it here at the denominator and this thing here. Okay, so you get this transfer function g of s is equal to 1 over s plus 2. Now if you need to obtain C of t, what you will have to do, you will have to multiply it here. Okay, so that will become C of s is equal to 1 over s plus 2 into r of s. Okay, r of s. If you have step input, you will be having 1 over s. Okay, so is this example clear, or you are just again confused? It's very simple. If you like, I would explain again it. Should I explain it again or go further? You have look, you have been given this differential equation, and you have basically the symbols are confusing you. Here C is basically y and r is basically x. Okay, so if you take the Laplace, you get s into C of s. Okay, s into C of s, applying the mask. Okay, Laplace transform, 2 into C of s, okay, equal to r of t, it will become r of s. Now take C of s common, that will become, yes, it will be s plus 2, and s plus 2 into C of s is equal to r of s. Now you know that r of s is equal to r of s multiplied by 1, so take it here at the denominator and this here. Okay, that will be C of s over r of s is equal to 1 over s plus 2. Clear? Now it's clear? Okay, good. So this is how you obtain the transfer function from any differential equation. Okay, now you have got the transfer function. Also try to understand the meanings of transfer function. Transfer function means this is the generic behavior of the system. This is your transfer function, and if you want a particular output, you will multiply this transfer function with your input, like take it here, and now you can apply impulse input, you can apply step input, you can apply parabolic input, and then you can check your response, C of s and C of t. Clear or not? Just take it here, take r of s here, and then apply the simple math. Like let me again explain to you some inputs we use in the control systems, like in the previous lecture. Now these are the inputs. If we have impulse input, like what is impulse input? It's like a punch. You have very large magnitude for a very small period of time, and its Laplace will be 1. Okay, and for the u of t means its value is 1 for t greater than 0. For t greater than 0, its value will be 1, and its value will be 0 for t less than 0. Okay, that is u of t, step function, we call it step function, and its Laplace is 1 over s. Okay, 1 over s. And next comes the ramp function. Ramp, like you have the ramps in your houses, ramp. Okay, slope, ramp in slope. Okay, like t into u of t, that if you apply 1 here, you get 1 here, if you apply 2 here, you will get 2 here. Its slope is 1. Okay, t into u of t, its Laplace will be 1 over s square. Okay, then you have the parabolic input here, like this is the parabola. So here you have 1 over 2 into t square. Why 1 over 2? Because you will be having 1 over s cube, its inverse Laplace. We will discuss it later. We normally keep up to here, up to ramp inputs. We normally, it's very rare, parabolic input, it's rare. Okay, so sinusoidal, this is very important. Sinusoidal, sine of omega t. Okay, you know that sine function, sine 0 0, sine 91, sine 180 0, sine 270 is -1, and then sine 360 is equal to 0. That is your sinusoid, and its Laplace will be omega over s square plus omega square. And if you have a cos of omega t, it will be s over s square plus omega square. You have to, again I would say, you have to memorize this function, this table. This table is very much important. Your life will be very difficult if you don't know about this table. Your life will be in trouble, in deep trouble, I would say. Like here, This table is very important, so please see it. If you have any question, you can ask. Let me now, okay. I think I should go to your notes now. Yes, your review. Now here we have f of s, that is the transfer function. It is n of s over s plus p1 s plus p2. This is real distinct poles. Real means these are real, these do not have any imaginary part, these do not have any oscillations. Okay, so it will be like k1 over s plus p1 plus k2 over s plus p2. It's generically, and we assume here also that it is a proper fraction. Proper fraction means the numerator is less than your denominator. That is the meaning of a proper fraction. So that will be k1 over s plus p1 plus k2 over s plus p2. Okay, so if you have 6 over s plus 1 s plus 5, you will be doing it like k1 over s plus 1 plus k2 s plus 5. Now cross multiply it with this denominator, you will be having 6 into k1 into s plus 5 plus k2 into s plus 1. Okay, is it easy to understand that how you get this from it? Okay. Yes. No. You want k1, what you will do? You want k1. No, you have make its denominator 0, make s plus 1 equal to 0. Okay, what will you will get s? If you make it 0, s plus 1, you can see that this term becomes 0 and you get only this term. 6 is equal to k1 into s plus 5, and s plus 1 equal to 0 means s is equal to minus 1. Okay, so here you will be having minus 1. So minus 1 plus 5 will be 4, and you will be having 6 over 4. Okay, 6 over 4 means 3 by 2. So here you get k1. Okay, now if you want k2, make this 0, s plus 5 equal to 0. So if you make this 0, this will become 0, and s is equal to minus 5. So minus 5 plus 1 is minus 4. So 6 over minus 4, that will be minus 3 by 2. So k2 will be minus 3 by 2. Is it easy? Okay, now put this k1 and k2 here. You will get 3 by 2 over s plus 1 minus 3 by 2 over s plus 5. Now take its inverse Laplace. Now you have to tell me that what will be the inverse Laplace. Let me open the yes, for this function, this. Yes, that is 3, that is wait. Here it will be 3 by 2 over s plus 1, and it is minus 3 by 2 over s plus 5. So its inverse Laplace will be 3 by 2 into e raised to minus t, because 1 dot t, it's plus 1, it from minus t. Okay, minus take this 3 by 2 common. Okay, it's common, take it common. E raised to minus 5, only minus 5. T. Okay, now u of t. So this is the solution, okay, of this inverse Laplace. Now you understand it. Let me show you some examples. It will be beneficial for you for the basic Laplace. Okay, these, for example, find the Laplace transforms of the given functions. Like f of t is 6 into e to the power minus 5t and is per 3t plus 5t cube minus 9. Is it visible to you? Now please tell me the first one. what will be its Laplace? Hmm. 1 over s, yes, good. 6 over s plus 5, 6 over s plus 5 plus here good, and we don't have any scalar here, we have 1. Okay, okay, plus now here no, here we don't have any exponential, it's t cube. I showed the formula. This is the formula of t raised power n. It's basically equal to n factorial over s raised power n plus 1 factorial. So what is meant by factorial? It's like no. It's like n factorial is basically n into n minus 1 into n minus 2 dot 3 dot 2 dot 1. For example, 2 factorial will be equal to 2 cross 1, 3 factorial will be equal to 3 cross 2 cross 1 equal to 6, 4 factorial will be equal to 4 cross 3 cross 2 cross 1, so that will be 24. Got? So that will be, for example, if you have now t cube, now please tell me, if you have t cube here, you have got t cube, so it will be 3 factorial s to the power 4. This plus 1 is with this n, it's with this n, okay. So 3 factorial over s raised to the power 4. So okay, so here you will be having 3 over s to the power 4, 5 into 3, 5 into 3 factorial, that 3 factorial will be 6 times into 5, that will be 30 over s raised to the power 4, okay. So minus 9, it will be minus 9 over s, because the Laplace of 9 cross 1, it will be 9 is basically 9 cross 1. So 1, the Laplace of 1 is 1 over s. 1 is basically the step function, okay. So this is the Laplace. You can see that f of s is 6 into s over s plus 5, s minus into minus 5 means s plus 5, 6 over s plus 5, and it will be 1 over s minus 3, and it will be 30 over s to the power 4, and it will be minus 9 over s. Is it clear? You must have to, if you have any doubt, please ask. If you have any kind of doubt in this transformation, basically this is Laplace transformation, you are learning it. So if you have any kind of doubt, no, it's from my it's my notes, these are my notes, I will share these with you, it's my slides numerical, okay. So I think it's useful, it made your concept very much better. So it's is it clear now? Move should I move forward? Okay, now please, it's up to you. If you want to, I can continue to the next hour, or is it if you want to stop now, I can stop. It's up to you. Okay. Yes. Okay. So case 1, case 2. Here I was is case 1 is clear to you now? Case 1. Okay. Now I come to the case 2, which is repeated. Basically, this is repeated pole. For example, s plus p1 square into s plus p2, like s plus 1 whole square. Two poles at the same location. So s plus p1 whole square into s plus p2. So how will you make its partial fraction? You just k1 plus k2 plus k3, k1 over s plus p1 square plus k2 over s plus p1, again p1 just power 1, here power 2, k1 and k2 plus k3 over s plus p2. This is the, no, that's bit different. No, there is square of a pole. Okay, there is square of a pole. So you have first k1 over s plus 1 p1 square, then yes, same thing. Now one thing here, one additional thing is here. For I told you that for k1 just make this equal to 0. Okay, if you make this equal to 0 or this equal to 0, it will result the same thing. Okay, if you make plus s plus p1 equal to 0 or s plus p1 whole square equal to 0, it will give you one coefficient, but you have two coefficients. So now you have to do compare coefficient method. You have to compare the coefficients of powers like s square, the coefficients of s square, or the coefficients of s, or the coefficient of a constant. You have to compare these to get one constant. Okay, you will not be able to get three constants with just letting equal to 0 these three things. Got my point? Okay, so for s is equal to minus 1, for example, you have this question 4 over s plus 5 whole square into s plus 1, that will be k1 over s plus 5 whole square plus k2 over s plus 5 plus k3 over s plus 1. So you cross multiply it, you get 4 into k1 into s plus 1, okay, plus k2 into s plus 5 into s plus 1, and plus k3 into s plus 5 whole square. Is it clear? Now if you take s plus 1 equal to 0, okay, if you make s plus 1 equal to 0, you get k3. Simply you get k3, okay, by making this equal to 0. Okay, only k3 is remaining, and that you get 1 by 4. Now make s plus 5 equal to 0. So here you will getting k3 0, at k2 you will be getting k1. You will get k1. Okay, you will get k1 is equal to minus 1. But now how will you get k2? It means you need something more. Okay, so for that, put the values of k1 and k3 here. K1 and k1 is minus 1, put it here, and k3 is 1 over 4, you can put it here, and then multiply it. It becomes like you can also do in a simple way, like comparing the s square terms. Okay, you will be having like these terms, like s square plus something, s plus this equal to something. So you have to compare both of these. For example, 6s square, you have 6, or to be very simple, you have, for example, in this example, 4 into 2s square plus you can say a square plus bs plus c. So c will be equal to 4. What? You have to compare the coefficients of same power. Here you have 0 dot s square plus 0 dot s plus, so a is 0, b is 0, and c is 4. You got point? That is compare coefficient method. Yes, for the s square you first have to find the where is s square. Here s square, because multiplied, this is s square. So here is k2 into s square, k2 into s square, and here you have s square because s square plus 25 plus 10s. If you expand it, a plus b whole square is equal to a square plus b square plus 2ab. So now here you will also be having the coefficient k3. Okay, so that will be k2 dot s square plus k3 dot s square is equal to 0 dot s square. You don't have any s square term here, it means it's 0. So k2 plus k3 equal to 0. Now you have k3 already, so k2 will be equal to minus k3. Okay, that will be k2 is equal to minus 1 by 4. So this is how, this is the repeated pole case. Repeated pole, you have the repetition, s plus p1 whole square into s plus p2. Just take some time to understand this. If you have any question, you can ask. Okay. Now case 3. Now this is the repeat. Yes, let's discuss this. Okay, minus 1 over s plus 5 whole square. So now take its Laplace. Now this is 1 over s square. 1 over s square is for the t. So it will be minus t into e raised by minus 5t. Yes, inverse Laplace. It's square. It's basically 1 over s square, but you have shifted the frequency. So here e raised by minus 5t. Okay, but it's 1 over s square. Therefore, it's t into e raised by minus 5t. Minus 1 by 4. Now here it is no, there are no squares, so it's a simple unit step. So that will be e raised by minus 5t, and 1 over 4 is 1 minus t. So here the point is where came the t, this t came from this. Again I will show you the table here. 1 over s square. Here look at this, look at this, look at this. Okay, okay. So yes. Okay, now we will move to the third case, that is the distinct complex poles. Now distinct complex poles means all poles are distinct, are different, they are not repeated, and they are complex poles. Complex poles means they have the term iota or j. Okay, in electrical engineering we have iota sign for the current, so that's why we model it as j. So can you tell me what's happening here? Yes, you can see the conjugate here, the steric. What does, yes, it's conjugate. Yes, change the signs of the iota. So this is a very special case, and you will not find it in book. It's in the notes. That this one thing is a good thing, though, because it's not present in the NS Nice book, but it's included in the notes. So that's a good thing. For it's way beyond the book. So okay, k1 over s plus p1 plus k2 over s plus p2. Now this is the conjugate of this p2. So you have to make the conjugate of k2. So k2 conjugate over s plus p2 conjugate. What? k1 over s plus p1 plus k2 over s plus p2 plus k2 conjugate over s plus p2 conjugate. Now what will be our next step? Cross multiplication. We will cross multiply it, and then we will find k1, k2 and k2 conjugate. Basically we have to find k1 and k2, and k2 conjugate will be just conjugate of k2. Okay, so this example, 1 over s into s square plus 0.2 s plus 1.01. So first you have to make the roots of these its roots are, you can even solve it with the calculator, it can be easily solved. Its roots are minus 0.1 plus j and minus 0.1 minus j. So here you get k1 over s plus k2 over s plus, basically the roots are s minus into this, so that will be 0.1 minus j and k2 conjugate s plus 0.1 plus j. Now cross multiply it, you get here 1 into k1 into s square plus 0.2 s plus 1. So how did you get this from this? Basically you are okay, you are multiplying with this, and s cancelled s, so you got s square plus 0.2 s plus 1.01, and for the k2 you got s into s plus 0.1 plus j, because one root got cancelled, its opposite one was this minus cancelled its minus, and you left with the plus 1, and here you left with the minus j. Okay, now put s equal to 0, you get k1, and put this thing equal to 0, you get k2. Simple. So if you get k1 and k2, for k2 if you get k2, now take its conjugate. These calculations are a bit tricky, because there are lots of chances of error in these calculations, like multiplying two complex numbers. So you can take the help from advanced calculator, like I have 991 fx 991 calculator. You should have practice. If you don't have practice of this, you will make errors in it. Okay, so what he has done the basic actually complex numbers you must be able to, yes, okay, good. Let me tell you something here. For the complex number, like if we have a plus a, sorry, a plus b iota, we can write it as r angle theta. R will be equal to under root a square plus b square, and theta will be equal to tan inverse b over a. So if you need to add two complex number, this form is good because you add real parts a1 plus a2 plus b1 plus b2 iota. And if you need to multiply two complex number, then this form is good because you just multiply the magnitudes and add up your angles like r1 dot r2 and theta 1 plus theta 2. Got? These two forms are very popular. You must need to know the two forms when you have to use this form for adding or subtracting complex numbers, and if you have to multiply, this form is good because it's the multiplication easier in this form. Got my point? Okay, so here you can see that here I have the real plus imaginary part, but here I got the answer in 0.498 3.04 radian. This angle is in radian, it's not in degrees. If you want to convert it degree, you have to multiply it 1 over 80 over pi, 180 over pi, 100, because 2 pi radian are equal to 360 degrees. Okay, you have calculator, yes, you can get from the calculator. So this is the angle and this is the magnitude, this is the r and this is your theta. And if you got k2, how will you get k2 conjugate? You will get k conjugate r, yes, it will be minus, it here it will be minus, angle will be minus, same magnitude but angle is minus. So now take the inverse Laplace 0.991, 1 over the inverse of 1 over s is 1, and plus this it will be e raised to the power minus 0.1 into t, and 2 into this whole, the inverse Laplace of this whole thing is basically, there are two things in it. For example, if you are, I try to understand it in a simple way, like for example, you are moving on a highway, you are in a car, and suddenly a speed breaker comes. What will happen if a speed breaker comes? You will move quickly up and down, and then due to the shock absorber you will get oscillations, and finally you become stable after some time you will get stable. So this is a response of the system. You can say it has two components: decay, that will be the decaying part, and the oscillations, the oscillatory part. So your system is basically consist of your decaying part multiplied by with the oscillatory part. So here if you take the inverse Laplace, you have the decay part e raised to the power minus 0.1 t, that one, it is minus 0.1 t, it's minus sign, with minus sign, and cause of what will be its frequency? You can see the frequency here, its frequency here you can see, here you have to determine it, the frequency you have got it 1 dot t, here you got it 1 dot t plus 3.04, that 3.04 from where you got that 3.0, it's basically your this angle is basically your here phi. We will discuss it further ahead because it will be some difficult for you to understand at this point. You and you multiply it with 2 and then 0.498, 2 into 0.498 e raised to power minus 0.1 t, and cos of omega t, its frequency, and plus 3.04 it's the angle, this angle. So this is the response of this system. Okay, so these are the three cases. Now further we have the mechanical system. We will I think we can we start now, or should we start in the next lecture? Okay, we will discuss it in next lecture. So so I'm stopping it. So thank you very much.